Hi, in this video, we are going to take a look at Lasso, Ridge, and Elastic Net regression in supervised learning. Okay, so linear regression, multiple linear regression, old school OG linear regression is absolutely the most foundational model structure that we have for predictive analytics, specifically for predicting a numeric target variable. Now, there's a huge problem. There's actually a lot of huge problems with linear regression. One of which is that if I have predictor variables that are like correlated with each other, like in a higher dimensional sense, collinear with each other, I can end up having problems with my model. I can end up overfitting. And this is the problem. So having predictor variables that I should have removed can end up causing problems in the fit of my model. Makes my model more complicated. Will make it longer to fit the model, and it'll be harder to interpret what's going on. Now, the most important thing to protect ourselves from this is to do feature selection. Feature selection, I go through and I say, hey, I want this predictor variable, not this predictor variable. I want this one, but not this one, and go through and just make wise decisions using subject matter knowledge, the constraints of my project, and like things like correlation, Kramer's V, association statistics to figure out what I should use, or like variable clustering. Variable clustering and correlation analysis was actually what I was doing at work today. All right, so sometimes it's just not even feasible to get through all the predictor variables. Let's say I have thousands of predictor variables, and it's a huge data set. And there's just no way for me to wade through this. It's just too much going on. I want some way to, in an automated manner, protect myself from overfitting. All right, so what we're going to do is that we're going to set up a scheme that when I do my linear regression model, I'm going to go through and I'm going to prevent the coefficients from being too big. What this is going to do is that I'm actually not going to fully fit to the maximum possible on my data. I'm not going to find the ordinary least squares aspect of the model. The coefficients are going to be reduced, so that way I'm not picking up noise that's in the in there. I'm not picking up the features that are in the training data that are not in the test or the general population. And so how we're going to approach this is that we're going to penalize our loss function for the size of our coefficients. Now, we're going to do this in three separate ways. There's going to be Lasso, which the penalty corresponds to the sum of absolute value of the coefficient. Ridge is going to be the 2 norms squared of the coefficients. It is going to determine the penalty. And then Elastic Net is a combination of Lasso and Ridge. All right, so this penalized regression models, honestly, they can do feature selection for me, and it also protects me from overfitting with multi-collinear predictor variables. Now, make sure you keep it in your head that penalized regression, its feature selection, is not a substitute for feature selection. We still need to do our feature selection. When I go through and I do that, I have several tools. First one is going to be subject matter knowledge. Another one is going to be constraint of my projects. Like if my stakeholders say you have to use a predictor variable, I'm going to use it even if there's problems with it. And I can use association analysis, and I can also use variable importance in a model. And so what penalized regression can do is that we can use the coefficients as feature importance, and with that we can like whittle things down and do feature selection for us. Lasso, in fact, will actually, for very low importance predictor variables, will give a coefficient of 0 and push it out. Ridge regression won't push it out. There'll always be a super small value, even if up to rounding it's 0. All right, so let's go ahead and use the house prices data set from Kaggle. And a previous video showed where you can get that. And I'm going to load my data using engine PyArrow so I can speed up the loading process. This is loading as a CSV, and specifying the data types. I have more control over how it's loaded. So like, for example, if I had social security numbers, I don't want those to be loaded as integer values, because then Python would think it's okay to do addition and subtraction. That's not the situation. So I like to have my data types correspond to what they actually are. And I could actually speed this up a little bit by putting in float 32, but I was lazy and didn't do that. But all my data has been prepared. I've gone through, I've done Yo-Johnson transformations on my predictor variables, and I've bended my categorical predictor variables. All right, so I'm going to have two sets of predictor variables. I'm going to call one the full list and one the reduced list. The full list is every single predictor variable I have available. The reduced list is going to be a subset of that. That from my prior evaluation of the predictor variables, it looks reasonable to use. I've kicked out some things that look redundant and look like they don't add further information given that other predictor variables are in the model. So here's a reduced list. You'll notice it's much smaller. And I've got floating variables, floats, so numeric predictor variables. I have binary, that is where there's 0 or 1. And you notice that these are mostly dummy variables. So all my categorical variables have been converted to dummy variables. Now, when I do penalized regression, it's important that we rescale our data. I want to have sample mean 0 and standard deviation 1, probably most likely when I'm dealing with real data. If I'm dealing with a situation where it's like pixels, I know the maximum, I know the minimum, dealing with pixels, 0 and 255 is the possible range, then I might want to change that to converting it to a 0-1 range instead, or maybe -1 to 1, depending on the nature of my data. Typically, in the type of problems that I work on professionally, I could have a new highest value or a new lowest value in the future. And so the 0-1 or -1 to 1 range doesn't work that well when I have like future values that might be bigger than what I've seen in my data or less than what I've seen in my data. And so you'll notice if I go through, if I hit the describe function and I limit it to the mean and standard deviation, it's not quite centered and scaled. It's pretty close. Honestly, I would probably leave it, but just to make sure you can see how to do it, I'll go through and do this. So this mean and standard deviation was set up by the Yo-Johnson transformation, and it's nearly 0 mean, nearly 1 standard deviation, but not quite. So just so that you can see, watching the video, can see how to go through and transform things to have mean 0, standard deviation 1. I'm going to use standard scalar from scikit-learn. And this, I'm going to specify my X. I don't have to specify Y, but I went ahead and did it because I have it anyway. And then so here, this object is an object for transforming data. And so what it's going to do, if I pass it a column of data that it was fitted on, it's going to take the mean of the fitted observed data, subtract it off, and then divide by the standard deviation. And so here I'm performing the transformation. If I'm going to be putting my data into a pipeline, this transformation has to be part of that pipeline to make sure I get things to work out the right way. And so now you'll notice I've got scientific notation, e to the -18, e to the -17. This is super, super close to 0. There is technically, from the computer's point of view, it's not exactly 0, but it's so darn close. Let's just call it 0. And practically speaking, we can see that the standard deviation is equal to 1. All right, so now variable importance. So when I do penalized regression, I'm going to get coefficients just like in regular regression, but with this system, I have a different method of figuring out what the coefficients are. In standard multiple linear regression, we're finding the coefficients that give me the least sum of squares value. Here, we want to minimize the sum of squares, but it's actually going to be a combination of a sum of squares minimization, but it's not quite, with an add-on penalty term. So it's going to be the sum of squares error plus a penalty term, put those together, minimize it, is what I'm trying to do with my coefficients. All right, so what we're going to do for variable importance, the absolute value of my coefficients is going to correspond to variable importance. And I can use regular linear regression for this same approach also, where I take the coefficients, but typically we want to have rescaled our data. With multiple linear regression, rescaling my data is not going to actually improve performance ever. That's actually a theoretical result. Now, in that situation, variable importance will correspond to the t statistic, absolute value, when I go through and do a hypothesis testing as a way for us to get variable importance. If I'm doing penalized regression, then it gets a little bit more complicated to do a hypothesis test, and frankly, just the absolute values of the coefficients is good enough for our purposes. Now, why do I need to rescale? Well, imagine that I have different coefficient magnitudes, not because of feature importance, but because of scale of the predictor variables. Let's say I have micrometers as one column and I have kilometers as another column. All right, so they're both distances, but they're on different scales. Well, kilometers, more than likely, just because it's because the numbers are going to be smaller, even though it's a much bigger unit, it's going to end up getting a larger coefficient for the predictor variable, more than likely. And so, but if I was to go through and rescale that so it was unitless, I would get a different magnitude of my coefficient. And so by rescaling things, I can get inconsistent coefficients off of there, depending on what I choose to scale. So if I was to have feet or centimeters, micrometers, kilometers, I'll get a different rescaled coefficient. And so across different columns where maybe I have a weight, maybe I have a mass, maybe I have a distance, maybe I have a temperature. In all of these, the coefficients are going to reflect what the unit of measurement is on the predictor variable. Well, in that case, I won't have that direct correspondence between variable importance and coefficient magnitude. So I need to rescale if I want to use variable importance. Now, also, if one scaling of a distance ends up giving me a huge coefficient, then what's going to end up happening when I do my penalized regression, if I had that unit of measurement, well, the model fitting process, I just had some thunder lightning right outside. That fitting process is going to pick up that large coefficient, and that's going to impact the fit of my model by how it chooses the coefficient. Now, if I switch it up so that another unit, same data, but rescaled, would end up giving me a very small coefficient. Well, that small coefficient isn't going to have a big impact on that penalty term. And therefore, the lasso ridge elastic net is not going to work to shrink that because it's so small. And so we want things to be consistent, and I want to rescale my values. So larger absolute value coefficients are more important when we're doing regular penalized regression. So Lasso will actually shrink the coefficients down to 0. And so when it gets down to 0, I know that I can kick it out. Now, when I'm doing ridge regression, which is minimizing the sum of squared values of the coefficients, will never actually kick it out. Will never actually give you 0 up to rounding, that is. And I can do feature selection by, well, if it's super small, I can just get rid of it because it's not important. Now, a nice thing about ridge, let's say that I'm in a situation that I must use a model, or I must use a predictor variable. I look at the predictor variable and it's not trustworthy. Maybe it's collinear with other ones I have to use. Maybe it's polluted. Maybe it's not trustworthy. Maybe it has no relationship with the target variable. And I want to get it out, but because of my project, I have to use it. I've been in the situation with models that go under legal scrutiny. And this was for HR annual evaluations. And because of that, I was like, hey, this variable is junk, but because this model for some reason is legally defendable, I have to keep this predictor variable in there. All right, well, you know what? I'm just going to bounce over to Ridge. Ridge is going to shrink it down. I don't have to worry about it so much. I get put on the stand, lawyer starts grilling me, say, hey, did you do exactly this model? Yes, I did. I had all those predictor variables. And also, collinear predictors can mute each other's importance. So if I had, imagine I had a variable, I put it in twice, okay? Literally copy and paste. And so in that situation, really the two together is going to be the overall of what I would have for just one of them for the coefficients. And so it's going to end up getting split. The coefficient gets split between the two of what I should have if I only had one in there, one version. And so what will end up happening is that if I have collinear predictor variables in there, they're going to look less important than they really are. How to address this? By doing proper feature selection and kicking things out that I don't want in there, or the ones that are redundant will help eliminate this process. If I do backwards elimination, this will also help address this. All right, so regularization techniques and hyperparameters. So Lasso, Ridge, and Elastic Nets induces a penalty on the loss function. The penalty controls the complexity of the model. So when I say complexity there, that's the size of the coefficients and reduces the chance of overfitting. The key hyperparameters are alpha, that's the regularization strength. The higher the value of alpha, I have the stronger the penalty, and the more the model will look to shrink coefficients down closer to zero. And then I'm also going to have a ratio of the elastic net regression. And this is going to be balancing Ridge and Lasso in elastic net. And typically we're going to use a grid search to help find the optimal parameters. In Scikit-learn performs cross-validation super fast. It's very nice. When I was in school, I learned about a formula for ridge regression that made it super fast. I've never seen one for Lasso, but something is definitely going on under the hood when you invoke scikit-learn. Somebody figured out something I don't know to get a super fast formula for Lasso. Now, expect the optimal penalty to be larger when there's more predictors. All right, the more predictor variables I have, the more opportunity for collinearity I have, the more opportunity for having redundant predictor variables floating around. And so because of that, expect to see when I have a large number of predictor variables to have a higher penalty parameter. Now, if the penalty parameter is 0 or practically 0, I could actually consider using linear regression instead. All right, so ridge regression. So here, what I'm going to be doing is we're going to take our coefficients, square them, add them up, multiply by the penalty term, and then add that to the mean squared error term of our formula. And this is technically not the mean, but this is what I'm going to be reducing. And so my goal is to reduce my squared error plus a penalty times the sum of squared coefficients. All right. And to implement this in scikit-learn, I'm just going to use either Ridge or Ridge CV, which stands for cross-validation. Ridge, I specify what alpha is, and it runs it. It isn't going to search for the optimal alpha. I'm starting out on this. I don't know what the optimal alpha value, the optimal penalty is, so I'm going to use Ridge cross-validation. If I knew what the alpha was beforehand because of somebody else working on a previous model, maybe I already did the cross-validation, I would go ahead and use Ridge and without CV and specify what the alpha is going to be. All right, so here I'm going to have my full set of predictor variables. I'm limiting it to the training data. And we can see that the penalty is about 55. All right, so let's visualize this. Here, the vertical axis is my mean squared error that I'm getting. And then the horizontal axis is the penalty term. And we can see that around 55 is where we have our lowest point. It'll actually start going back up if I went through a larger range. So, I evaluated from 0 to 60 on this. Now, if I do the same thing, but now it's with the reduced data set, you can see that now I've got about 17 as my penalty parameter. And so we can see that my mean squared error starts out high if I had 0, comes down to the low point around alpha of 17, and then starts climbing back up. Now, if I want to do variable importance on this, all I do is just take my coefficients and just consider them. Now here, I'm not going to take the absolute value because I want to be able to double check my model. We always want to make sure that I have negatives and positives of coefficients that make sense whenever I have a regression model of any way, shape, or form. All right, and so remember, if it's low, typically on these categorical predictor variables, the low bins were the ones that had the lower average sales price. And so I would expect to see a negative value. All right, and so now as I scroll down, we get down to here, we see ground living area, overall quality, neighborhood, garage, overall condition, and so on, have the largest positive coefficients. And so we can scroll through and we can see how important the model says each predictor variable is. And so if I was to remove a predictor variable, I would say total rooms above ground could probably be removed. Now, here, this is probably collinear with other predictor variables. Total rooms above ground are probably going to be corresponding to the living area above ground, pretty well correlated, but it might have informative value. So I might want to consider removing that, or lot frontage. Lot frontage is definitely correlated with other features in this data set. And all these are rescaled also. Now, lasso regression is similar to ridge regression, but now you'll notice that my penalty is going to be based on the absolute value of the coefficients. All right, so let's go ahead and run through the same thing. I'm going to do cross-validation on Lasso to find the optimal penalty parameter. And so here, this is very small. Oh, okay. So this is interesting. If I look at this, this is pretty close to 0. An alpha of 0 would be no penalty term. So I might want to use regular old linear regression instead of Lasso. Now, if you're thinking about using Lasso or Ridge or Elastic Net to fit a multiple linear regression model, you can do that. You can set alpha equal to 0, but the documentation tells you don't do that. Just go ahead and go straight to multiple linear regression, because that model is the software is tuned and built up for that type of modeling. If I use Lasso or Ridge or Elastic Net with a penalty of 0, technically it's going to be like a pencil and paper, exactly the same as linear regression, but the software implementation is different. I'm not going to get all the full power of multiple linear regression, so I don't want to do it that way. All right, so here I'm going to have the full set of predictor variables. And you'll notice, so I have a very small penalty parameter, and you'll notice that we start out very, very small penalty, but then boom, I jump up to a higher penalty and then it flattens out. All right, so what has happened here is that the coefficients were kicked out. Once I got to a high enough penalty parameter, the model just went and kicked everything out, and it went to a constant model of the intercept. This is the intercept model over here. And so I don't want that. And so, I probably would not be putting Lasso into production. I would instead go into multiple linear regression instead for this particular example. All right, so now let's do the same thing, but this time with the reduced set of predictor variables. And I can see exactly the same thing happened, that I have a very small alpha. So it's really, really close to being multiple linear regression, but not quite. And once the penalty got just a little bit big, boom, it kicked out everything and went to the intercept model to minimize the sum of the absolute coefficients. And so I would be leaning away from Lasso off of this. I would look to multiple linear regression instead of Lasso if I could. And now here, you'll notice when I look at the coefficients, I have actually zeros, at least up to rounding, on my coefficients. So effectively, what this is saying is that these predictor variables, I could just completely kick out from the model and I'm not going to lose anything. And so like future performance on the model, well, I want to kick out as many predictor variables as I can because fewer predictor variables makes it easier to understand, easier to interpret, makes it faster to train, faster to fit. Also, in the future, when data is coming in, the more predictor variables I have, the more opportunities for failure. So let's say in the future, I run my model and I included lot frontage. But for some reason, my organization stopped recording lot frontage or it was missing. Well, that's a problem. I have to deal with it. The fewer predictor variables I have, the less opportunities for failure I have from my data as they come downstream as I run my model in production later. And we can see, we have a pretty similar ordering of variable importance. Not exactly the same, but I always want to go through and check to make sure that negatives and positives make sense. And also I want to check to see, do I have any predictor variables that are crazy, crazy big compared to anybody else? All right, so now for elastic net regression, what I'm going to do is that I'm going to have like a balancing of the ridge penalty and the lasso penalty. And so we're going to have the L1 ratio. This doesn't really look good in the math equation LaTeX, but this is what it's called in scikit-learn. It's called L1 underscore ratio. So I present it this way in the formula to be consistent with this. And so you can see we have a weighted average of the coefficients squared with the absolute value of the coefficients. And then I multiply by the penalty term. Right, and that ratio is between 0 and 1. If I had 0 for the ratio, that would be ridge. 1 for the ratio, I would be doing lasso. And in those situations, I would not want to actually do 0 or 1, because if it's 0 or 1, I actually just want to use ridge or lasso proper, because the system is just built up to handle those better. The implementation is going to be the way I want it. From a pencil and paper theory point of view, there's no difference, but in the software implementation, there is. All right, so let's go ahead and run through this. I'm going to build up a bunch of ratios. I'm going to put them into an array. And you'll notice I have the exact same alpha values, and I have my ratios passed in. I had to increase the maximum number of iterations for scikit-learn not to give me a warning message, by the way. All right, so here I can see what looks like the minimum alpha. All right, that's close to 0. That's close to 0. So this is saying that I might want to instead put in a 0 there, and that 0 would be, in fact, regular old multiple linear regression. That might be a better choice for what's going on. Now, my ratio is about 0.6. So we're setting it up so that we have 0.6 times the ridge version times 0.4 times the lasso version of the coefficient penalty term. All right, so now my fitting involved alphas and ratios, so the penalties and the weighted average parameter. And so that's going to be a grid. So let's go ahead and do a heat map to take a look. So here is the penalty term, and I've got the index along that array. Here is the ratio index going through. And so now I can see that this is showing a smaller ratio, and is up here, and the alphas are all along this. Okay, so let's go ahead and so we can see 0.01 for alpha, and then here is the ratios. And I can do the same thing for the reduced. And now you'll notice that, look at the gradient here, the red, white, and blue. Look at the gradient here. It's a little bit different with the reduced. but we end up seeing a ratio of close to 0 for the parameter there. And once again, we have a very small penalty term. All right, so close to 0 for the ratio. When I look at that up here, that's saying that I would be looking towards Lasso. This model is very, very close to being a Lasso model, but not quite. And then once again, I can get my coefficients. I always want to double check to make sure that the positive and negative aspects of my coefficients make sense. I want to, because I'm using this for feature importance also, I can use this to consider removing predictor variables. So like year built, I might want to get rid of. And you'll notice that the same values tend to pop up in the same positions. It's not exactly the same, but pretty close, consistent ordering. All right, so now let's talk about cross-validation. So in cross-validation, I'm going through and I'm trying to find the best parameters for my model. And my goal for this is to be able to make the best predictions possible on unseen data. And this is true for any model structure whenever I'm determining the parameters. Now let's go ahead and compare the models across their training, validation, and test sets. Okay, so if I go by the training data, it looks like the elastic net reduced is actually the best performing. If I go, but you'll notice that it's not really that big of a difference. They're all kind of tight with this, and this is the mean squared errors. When I look at the validation, we can see that elastic net full did a little bit better. And when I look at test, Lasso reduced is the best, but you'll notice it's not really that big of a difference. They're all kind of in the same ballpark. And so which one would I pick? Well, it would depend on my project. I would honestly probably lean towards using Lasso because Lasso kicks out predictor variables, and that's a simpler model. And I would actually go through and refit after removing those predictor variables from there. Now, another thing I also want to check, to see, do I have a big gap between training validation and training and test? If I see that training is much smaller than validation, or I see that training is much smaller than test, that's an indication that I have overfitting. All right, well, here I can see that's actually bigger on most of them. If it's not bigger, it's close to it. Like, that's actually bigger. I'm comparing to validation first. All right, so here it's a little bit smaller than the validation, but they're all pretty close to each other. So I feel like I'm not in a big risk of overfitting with this particular model. All right, so in conclusion, Ridge minimizes the coefficients by penalizing the sum of squared magnitudes of the coefficients. Lasso minimizes the coefficients by putting a penalty on the sum of the absolute value of the coefficients, and then elastic net is a weighted average of those two sums. And that's how we get our penalty off of that. So for your homework, go out and apply Ridge, Lasso, elastic net, and try different penalty parameters. Try different different alphas, and just see what happens. See what happens to your predictor variables, their coefficients, as you increase that penalty and as you decrease the penalty. And if you want, go ahead and compare to multiple linear regression. All right, well, that's all I've got for you. Life is short. Do math.